All right, so quantum physics. We're diving into a world where, apparently, even the greats had some trouble. Huh. You wouldn't believe the stack of research I've got for this one.
Well, it's true. Even Richard Feynman, a giant in the field, admitted that quantum mechanics can make anyone scratch their head a little.
Let's be honest. That's both a little comforting and intimidating at the same time. I mean, if Feynman found it tricky, does that mean I'm doomed? But, seriously, where do we even begin with this stuff?
The best place to start is by understanding the scale of things. See, our everyday world, all the stuff we see and touch, that's classical physics. Quantum physics, that's the rule book for the really, really tiny stuff. Atoms, particles, all that.
Okay, so different rules for a whole different world.
Yep.
But how did anyone even realize those rules existed? Didn't they think, back in the 1800s, that physics was basically solved?
That's what they thought. Lord Kelvin, a big name back then, even said there was nothing new to discover in physics. Can you imagine?
Talk about speaking too soon. Okay, so something must happen to shake things up.
Oh, absolutely. And it wasn't just one thing. A whole bunch of experiments basically flipped the script. One of the biggest game changers was this thing called the photoelectric effect. It showed that light, which we always thought was a wave, could act like particles, these
Yeah.
things called photons.
Wait, hold up. Particles? Like tiny little bits of light instead of waves.
Exactly. Picture it this way. They were shining UV light onto metal, and this was making electrons fly off the surface.
Okay, that makes sense so far. Brighter light, more energy,
Yeah.
electrons go flying.
All right. But that's not what happened. Turns out it was the frequency of the light that mattered, not the brightness. The color, basically. Even weirder. Below a certain frequency, nothing happened, no matter how bright the light was.
Now that just seems wrong. Like, a dim blue light can move something, but a super bright red one can't? How does that even work?
That's where Einstein comes in. In 1905, he proposed this radical idea. Light isn't just a wave, it also exists in these little packets of energy, these photons. And the energy of a photon, that's tied to its frequency, not its brightness.
So you're saying one brief photon, it's got enough energy to knock an electron loose, but a red one, even a whole bunch of them, they might not do anything.
Exactly. It was such a big deal, Einstein got a Nobel Prize for it in 1921. Light wasn't just a wave anymore, it was also these little quantized packets of energy.
Whoa, talk about a plot twist. But that was just the beginning, right? If light could be both wave and particle, what about, like, matter itself? Could an electron, which seems like a solid little thing, also act like a wave sometimes?
You're onto something. Turns out, yeah, even matter can have this split personality, and the way they figured that out was totally unexpected. It involved a lab accident.
A lab accident. Now that's what I call a good story. Tell me more.
So there were these guys, Clinton Davison and Lester Germer, working at Bell Labs in 1925. They were studying how electrons bounced off a nickel target, and then, well, a bottle of liquid air decided to go boom. Busted up their equipment a bit, including their nickel target.
Yikes. Hope everyone was okay. But I have a feeling this mishap led to something interesting, right?
It did. To fix the damage, they had to heat up and then cool down the nickel. Totally by accident, this made it crystallize. Means the atoms all lined up in this neat and orderly pattern. So they run the experiment again, and get this. The electrons they were bouncing off the nickel, they formed a pattern. But not just any pattern. This was a pattern only waves could make.
Hold on, are you saying those electrons, those little particles, they were acting like waves? Like diffracting through the crystal, just like light waves do?
Exactly. Classical physics couldn't explain it. Electrons, particles of matter acting like waves. This little accident ended up proving a hypothesis by this guy, Louis de Broglie.
Okay, hit me with it. What did de Broglie propose?
So he said that matter, specifically electrons, could have wave-like properties. He even came up with an equation for it, connecting an electron's momentum to its wavelength. We can dig into that a little later if you want.
So we're talking about, like, a fundamental duality here, right? Light, which should be a wave, can act like a particle. And electrons, which are particles, can act like waves. What's going on, universe? Why are you going to make things so complicated?
It's definitely a head-scratcher, but that's wave-particle duality for you. One of the biggies in quantum mechanics. Completely changed how we understand the universe. We used to think things were either waves or particles, nice and neat. Not so much anymore.
So this isn't just some, like, theoretical thing, right? This actually changes how we see reality, doesn't it?
Oh, absolutely. And it's not just theoretical physics either. This wave-particle duality, it's the backbone of a lot of technologies we use every day. Smartphones, lasers, medical imaging, all that stuff.
Get out. So all that stuff relies on a theory that, let's be real, Still sounds kind of like magic.
It kind of does, doesn't it? And we're still figuring out all the possibilities. Like there's this whole field, quantum computing, where they're trying to use these wacky quantum rules to build super powerful computers. Imagine what we could do with computers like that.
Okay, now that is cool. Quantum computers, I've heard the term, but it always seems so far out there. They're really that powerful, huh?
The potential is mind-blowing. But it's not just about, practical applications. Quantum mechanics, it makes us ask some really big questions. Like, what does it mean for something to be both a wave and a particle? What about the observer? Do we influence things just by looking at them? How much can we really know about how the universe works at the most basic level?
Whoa, okay, those are some deep thoughts right there. Definitely makes you think. But okay, let's back up a second. We've established that this wave-particle duality is a thing. But how does it actually work? Can we, break it down a bit?
Of course. To really get into it, we need to talk about one of the most important ideas in quantum mechanics, the wave function.
Wave function. Sounds kind of mysterious. Let's deal with this one.
It's basically a way to describe a quantum object using math, but instead of telling us exactly where a particle is, it gives us the probability of finding it in different places.
Probabilities. So it's like there's a chance it's here, a chance it's there, that kind of thing.
Exactly. Instead of a tiny ball, imagine like a cloud of possibilities. That's the electron. The wave function just tells us what that cloud looks like, where the electron is most likely to be when we try to measure its position.
Okay, so it's not that it's actually in multiple places. It's
Yeah.
more like we just don't know for sure until we look, right?
That's the crazy part. It doesn't really have a definite position until we measure it. It's in this weird state called a superposition, meaning, in a way, it's in all those possible positions at the same time, or at least the potential is there. But when we observe it, when we measure it, the wave function collapses, and then the electron has a specific location.
Hold on, are you saying it just by looking at it, we're kind of forcing it to pick a spot? That's kind of wild.
It's definitely a mind bender, and it's something people are still debating about quantum mechanics. Seems like the act of measuring, of observing, it actually influences reality at that level.
Okay, that's just wow. But let's go back to the wave function for a sec. You said it tells us the probability of finding a particle. What determines those probabilities? Is it totally random?
Not random at all. The wave function, its shape, it's all determined by the particle's energy and the forces affecting it. It's got its own unique wave function, like a fingerprint.
Okay, so it's not all chaos down there. There are rules, even if they're kind of weird rules.
Exactly. And by understanding those rules, by understanding the wave function, we can actually make really good predictions about how quantum objects will behave, even if we can't know everything for sure beforehand.
This is definitely a lot to take in. Makes you wonder what else is out there, what else we might discover about the universe through quantum physics.
Oh, we're just getting started. Remember that idea about a civilization existing at the atomic level? Imagine if they suddenly encountered our world, the world of classical physics.
I bet it would blow their minds, just like quantum physics blows ours.
Exactly. The way we understand things, it's all based on our experiences in this big world. But at the quantum level, things work differently. It's a whole new way of seeing reality. And who knows what we'll be able to achieve once we really start to understand it.
Now that's a thought to end on. Imagine the possibilities if we could really harness the power of the quantum world. It sounds like we've got a lot more to explore in future deep dives, that's for sure. Thanks for joining us on this wild ride into quantum physics, and we'll see you next time.